So I wanted to make a video about this magic square of squares problem, which they say is probably impossible. So what they're trying to do is they're trying to make a magic square, which is where all the rows and columns and diagonals add up to the same number, but they're trying to use only numbers that are being squared. On these videos you'll see the Parker square, which is like this, where you can see all the numbers are being squared. And all the columns and rows add up, but one of the diagonals does not, and it also has a repeat, and it's supposed to have all completely different numbers. So it's like close, but it's not exactly there. There's a few others here that are close, but aren't exactly there. You can see they're missing numbers, or one of the diagonals doesn't add up. This one's pretty close. It's called Salo's square. I think that's how you pronounce that, but he did a lot of work on it. And I'm going to show you that in a second here, but you can see one of his diagonals doesn't add up, and I can tell you why that is too. So Salo's has their own website here where they have this paper called The Lost Theorem, and you can get a PDF of that. Now in that PDF it's going to go over the standard formula on how to make a 3x3 magic square, which doesn't work when you square the results. Then it goes into parallelograms and Argand diagrams, each representing a magic squared, as you can see on the Wikipedia page. But pay attention to this little square of squares down here with the letters in them, because that order becomes important when you compare it to the equations for each equation that you're going to get out of the 3x3. And the paper goes on to talk about the most standard, 3x3 magic square not squared. But this square and these combinations of the letters are pretty pinnacle. So let me show you what I did with that. As you can see, I start with that same square and I go on to the combinations and how many times each letter is going to be used. So the M is going to be used 4 times, the V is going to be used 3 times, the T is going to be used 3 times, the W and the U are going to be used 3 times. That's because V, T, W, and U are the corners and M is the very middle, and all the other ones get used twice because they are the side and top and bottom pieces. And I know this is hard to see, but they sort of plot out like this, where there's these 2 groups here that you can see have other groups that are coming off of them and 2 that are not, and that's basically what's happening off your centerpiece M, but I'm going to go more into that in a bit. So what I have here is a diagram of a magic square of squares. At the top here you can see that, let's say it's a number ending in 1 being squared, and then a number ending in 4 being squared, and then a number ending in 5 being squared. Same thing with the top row and the 2 and the 3. What that would become is a number ending in 1, and a number ending in 6, and a number ending in 5, which when you add them together, the last number would certainly end in a 2, and then for the 1, the 4, and the 9, the last number would certainly end in a 4, and because the last numbers are different, that would let you know that the sums are for sure going to be different, regardless of what the numbers actually are, meaning that you can solve the problem just by looking at the last digits. So from there, what we can do is we can take any number ending in 0 through 9, because every number ends in 0 through 9 in base 10, and then we can square that number, and we know that it for certain will end in 0, 1, 4, 9, 6, 5, 6, 9, 4, 1, which repeats. So that actually becomes a set of just 0, 1, 4, 5, 6, 9, meaning that any number squared will end in 0, 1, 4, 5, 6, 9. And what that means is you could try to make a magic square, a regular one, not a magic square of squares, but just a regular one of those numbers. Because, like I said, if the last digit doesn't add up, then certainly the whole number does not add up to the same number. And so I asked this question, admittedly on the wrong forum, puzzling.stackexchange. And as you can see here, someone actually used my set here to come up with solutions, and they found 14 solutions, although 6 of them were trivial because they just repeated the same number. Which the answer turns out to be this pattern right here, where you will notice that it has the diagonal 5s in one direction or the other, which is really just saying that you might as well just pick one or the other. That really just ends up being these combinations here. And you can write those combinations. Obviously, you can flip them. You can rotate them. They're like symmetrical. But these turn into the 8, and the other 6 are just using all the same number. And so with that, you could do all the numbers have the same last digit so that they necessarily add up. Like, let's say, for example, it was like 51, 31, 41, whatever, just a number ending in 1, then for sure they would always end up to the last digit being 3. Same thing, you could do all ending in 0, but then I suspect that the following digit before that is going to become the issue, but because of how squareds add up, that's actually something that I need to look into. That could be maybe an area that we might have a solution, but I'm going to go on to all the other ways that I've checked based on everything but that. So let's say we take this pattern here with the diagonal 5s and the 1s and the 9s the way they are, because that is how this equation here would have to be applied because of the last digit after all digits are squared. If you can remember back to when I was just saying that is kind of a necessary part of what's going on here because the last digit has to add up. Keep that in mind. But again, if we take this pattern here, let's see what that would look like. Well, you could do 5 squared, 5 squared, and 5 squared as the diagonals, and then you could do 1 squared. 7 squared ends in a 9, so that's how it's going 1, 9, 9, 9, 9, 1 kind of deal, like where it's the same as the other one here. It's kind of hard to remember because you need a 1, 2 9s, 2 9s, and a 1. Well, so these are the 2 9s and the 1. Okay, so it does get confusing what I'm trying to say here. So let me try it one more time here. Bear with me. Which is that, like I was saying on this page, after it's squared, it has to have 9, and then a 1, 1, and then the diagonal 5s, then 9, 9, and then the 1. Come back here, right? Okay, so this is the same thing, but just kind of reversed. It's the 1, the 9, 9, because 7s ends in 9s, and then the 5s, and then the 1, 1s, and then the 9. So it's the same pattern. But this adds up. This all adds up to 75, because 49 and 1 is 50, and then 25, and that's 75, which is the same as this. So that works right there. But you can see it's 3 numbers repeated, so it's not really a magic square of squares, because all of these numbers would have had to have been completely different from each other. And I can show that even better when you do triple 5s, triple 1s, triple 7s, it still works. The number's like 9 billion and something, or 9 million and something, but you can check it out for yourself. Okay, it's actually 924075, and I'll show the calculations for that on the screen right about now. Here we go. That should be enough time. Now, using this pattern, I was actually able to make other ones here, which is diagonal 25s and 31 and 17. Again, that's just 3 numbers repeated. So that's not exactly what we're looking for. We're looking for all different numbers, which means these diagonals have to be different, and then these numbers have to be different. Now, I really don't think that it's going to work just intuitively off of if you were to take medium, high, and low and permutate it like we were doing before. You're going to get these diagonal mediums that have to add up to the same as a medium, low, and high. That might be possible, but that's really what we're looking for. And just a little quick recap, that means we're taking A and B and A, B, and C, and we're trying to spread them out as best we can. And when we do it with like a tic-tac-toe cats game, for example, you'd get a BBA, A, B combination. That would not work because they would add it differently based on the last digit necessarily, like odd, odd, even, 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 odd, right? Odd, odd, even always is even, and even, odd is going to be odd, so that's not going to be the same last digit. And so here is where it's the same as the medium, high, low thing, where 3 mediums are going to have to equal a medium, high, and a low. Again, not to repeat, but that's because you square any number, it only goes to these numbers. You could use all the last number, etc. Because, again, you're trying to make a magic square with just these sets that fulfills these equations, with the m being used in 4 equations. And I mean, that's where I really started with this problem, was just the basic formulas and then looking at evens and odds and looking at what square numbers always add up to on the last digit and stuff like that. Okay, now let's get into the meat, the data. Okay, so with what I've told you so far, you know that it has to be odds like a 1 or a 9, and a 3 or a 7, and 5s, and it has to be arranged in this pattern, like a 3 and a 7 are going to square to a 9, and a 1 or a 9 are going to square to a 1. Or you have the evens here, the 2 and the 8, with a 4 and a 6 and a 5. Why? Because a 2 and an 8 are going to square to ending in 4, and a 4 and a 6 are going to square to ending in a 6, and that's going to add up on the last digit. So that's why I have a tab for each of those. And then I have a tab for ending in all the same digits. Except for 0. I didn't do 0 because I suspect the problem would come from the number before that, but now I'm rethinking that and I'm going to check 0 on maybe a part 2. Let's look at a problem that there is with evens and 5s not adding up. So, try not to be too shaky here, but if you look over here, you'll notice the numbers never end in 75. And that is going to be a number ending in 2 or 8 being squared with the number ending, it's squared and then added to a number ending in 6 or 4 that's getting squared, and a number ending in 5 that's getting squared, and all three of those are getting added up to a total over here. And so what you'd want to find is multiple of them that are adding up to the same total. Sorry, I had to sort that for you. So when you sort it by the same, size numbers, ascending order, then you can find where all the totals get to be the same. So these combinations are these totals. And so that is where you're going to want to look for numbers being used more than once. That goes back to how M is being used 4 times, W is being used 3 times, etc. As you can see here. Which I wrote this way because it's a little easier to understand that M's going into 4 with each one of the other letters, and then the other letters are being combined their own way, which adds up to M being used 4 times, V, T, W, U being used 3 times, Q, P, R, S being used twice. So that's what we're looking for over here, and what we're essentially looking for is in this column over here, we want to see that it has the same number repeating a lot of times, and so that it has multiple combinations. And you don't really see that with this one whatsoever. And really, I can tell you another reason why evens and a 5 is going to be a problem is because if you go over to just 5s, and this is just permutating squares of 5s, they always end in 75. And so that means any 3 numbers ending in 5 squared and added together are always going to end in 75. Whereas you can see any 2 even numbers and a number ending in 5 squared, they're never going to end in 75. So you know for sure that that is not going to work. Why? Because for the last digit to add up, they have to be like this or like that. And so if they're not adding to 75, that means that these diagonals are going to be adding to 75, but these are never going to be adding to 75. Let's check on odds here and 5s. And then you can see here's some odds and a 5s, and they are ending in 75, so that is possible. So then you'd say like, okay, 104, 75, which I made another list next to it. Admittedly, it's smaller, and it has 104, 75, and it is just combinations of numbers that end in 5. So that would tell you odds and 5s is a possible chance to work. That's basically numbers that after they square, the last digit is going to be these digits here, which is necessarily combinations of 1 and 9 and 3 and 7, because when you square 1 or 9, you get a number ending in 1, and when you square 3 or 7, you get a number ending in 9, which is how you would end up with these 1s and 9s and the diagonal 5, which would all add up to a number ending in 5 at the end, specifically a number ending in 75. But again, my issue is none of these numbers are being used 4 times over. It's always the same combinations. Like if you look down at 95, 55, and 45, go up to 55 and 45, you just have 95 and 45. Again, it's the same combination, just written a different way is all, because it's permutating. So what you're going to be looking for is these numbers to be repeated many times, 8 times at least, so that you get 4 different combinations when they're repeating. Which I know that's kind of complicated, and that's because I didn't remove duplicates for my permutation, but this is keeping them in for the chance that maybe if you doubled one of the numbers it would work or something like that. Like if you used a number twice that it would work. Which I mean is basically just looking for a semi-magic square that gets a little closer than maybe the Parker square. Like when you come to this in the data, you can see that's 2 combinations, 95, 85, and 5, 95, 65, and 55. So you're looking for that to be more like 8 of them. That's really 4 combinations. Let's say that we did find one number being used in 4 combinations, like 175 here. It's being used with 5 and 285, 75, 275, 105, 265, and itself and 225. Now with itself kind of sucks because that means there's probably a repeat in there, right? Which we don't want, but that's about the best that you usually find. You don't usually find more than that. I've been looking, I haven't found it yet. As you can see, they're all the same total. Then what you'd want to do is say that 75, right? You'd want to go up to 75 and say, does 75 have multiple combinations? It does. It has 2 combinations. That's good. But what we know is 1 has to be used in 4 combinations, 4 of them have to be used in 3 combinations, and 4 of them have to be used in 2 combinations. So can we find any of these numbers being used in 3 combinations? Well, we kind of can. If we go down to 275, we notice that it's being used in 3 combinations here, but we also notice that this never happens again. None of the other numbers are being used 3 times over, so that doesn't work. 75 is being used twice, so it only gets us really halfway there. Let's say that we go back and check the odds, right, to see if that could possibly fill in the gaps. Well, what you can see here is that none of the numbers are being used in multiple combinations. Well, 45 is being used with 7 and 99 and 97 and 21. Same with 65. So maybe that's something that I want to try to work on too, but I really don't think that that's going to work out. Because again, I have to put it in this format, or it all has to be ending in 5. And I have to find one that's being used in 4 combinations, 4 being used in 3 combinations, and 4 being used in 2 combinations. But it's like only 3 being used in 2 combinations here with the odds and the 5s. And like I said, there's only 1 3 combo here and 1 4 combo here. And so, you know, it doesn't work out to being what it needs. And you know, with these permutations, it's 27,000 options. So, I mean, maybe if I did more permutations, it might work out better. Because, I mean, it really just adds more combinations at the beginning. Like, you know, 5 with 295 could have been 5 with 395 and so on. And then there's checking with if they all end in 0 but have a number before, if that's just the same problem yet again, but 1 digit before or not. Kind of exploring that. And again, it's trying to get these odds and 5s ending in 75 to sort of fit together in this square here with these equations. So I started to think that these 2 equations were going to be the most important. Like your number ending 5, your number ending in 5, and your number ending in 5. That's the first one you want to dial down. Then you want your third number ending in 5 with your x2 and your x4, and how that really looks like is like, let's say you lined it up like this. Your number ending in 5, your x1, your x2, your x3, your second number ending in 5, your x6, your x4, your x5, and your number ending in 3. My point here is you want to get your diagonal and then your 2 corners, hoping to fill in the top, bottom, and 2 sides last, is kind of what I'm getting at. Which I know a lot of this stuff is really hard to read and looks like garble, but it's sort of a way that I pieced my way through, you know, what would be the best plan of attack. But ultimately, I'm happy about my smallest 1-digit semi-magic square of squares. That I turned into a bigger one. But ultimately, figuring out the last digit thing's been the best thing I've got going so far, and how they have to add up, which leaves only these possibilities. which someone else did the hard math to figure that out for me. On the wrong forum, of course. And I mean, this is a part 1 video, and the way that they're trying to solve it is with geometry and graphs and higher dimension projections and things like that. So it's way different than how I'm going about it. It's worth noting that they mentioned Pythagorean triples. There's also Pythagorean quadruples, a squared plus b squared plus c squared equals d squared. And then they also mentioned that every number is the product of 4 squared numbers, which I imagine somewhere in there might be the proof that it's possible or not as well. And I'm imagining the reason is because when you actually get one number being used in 4 combinations, that you never get another number being used in 3 combinations or more. So I mean, like 275 was 3 combinations, but none of these other numbers had 3 combinations. Oh yeah, and I think I forgot to mention that you probably couldn't use all the same number in combinations with 0 because you go back to the BBAAAB thing. But anyhow, there's a lot of different ways to look at it, but focusing on the last digit was sort of where I started on the whole problem and everything. And so this is a part 1 video. I might make a part 2. I did not show my face because I have an infected tooth that is making my face swell. And it's Sunday and I'm kind of in my PJs. But yeah, I hope you enjoyed the video, and maybe you can comment with more ideas that you have on this idea or this problem. But I'm probably going to give this problem a rest for a little bit because I've really thoroughly checked into it. Maybe I'll have to find a better way to permutate these options, but yes, I've definitely looked into it. Only got a little more looking to do. And so thanks for watching and have a great day.